Welcome back to Family Feud. Today we have the Euler family and against the hospital.
No! Steve, actually it's Euler and L'Hopital.
Okay. All right then. Let me quickly explain how the game works. Researchers have been out on the streets asking a series of questions, which will be asked to the families. Whoever answers quickest and is on the board will either play or pass. The round continues until all the players on the board are found, or 3 misses will pass it over to the next family. Fill in the rest of the word. Mac, blank.
Mac and cheese.
Number 1 answer. You want to play?
Absolutely.
All right, Damien, what do you think?
I'm gonna go with Macklemore, Steve.
That's up there.
What about McDonald's?
Mick, not Mac. Not up there.
What about McLaurin?
Where's McLaurin? Oh, that's up there. Sorry.
McLaurin series, aka Taylor series with the training wheel still on. So picture this. You have a function like e to the x cosine to the x, or even sine to the x, and you're like, hey, function, I see you being all curvy and nonlinear, but I want to approximate you with just polynomials. And the function goes, cool, I can do that, but only if you know my derivatives. So a Maclaurin series is f to the x equals f of 0 plus f prime of 0x, and on and on and on. A Maclaurin series is f to the x equals f of 0 plus f prime of 0x plus f double prime of 0 divided by 2 factorial multiplied all by x squared, and on and on and on. The one thing that makes Maclaurin series different from Taylor is that it's centered at 0 always. It's like building the function from scratch using an infinite sum of derivatives at 0. It's so elegant. It's like building Legos if Legos had a tutorial.
Great, guys. That's all the answers on the board. Okay, your question is things that have lefts and rights.
Blinkers. Hands.
Blinkers is the number 1 answer. Do you want to pass or play?
Play.
Okay. Joey, what do you think is up there?
Political views?
That's up there.
I think shoes.
That's up there too.
Cars?
No.
Give me roads.
Mm-mm.
Outfields?
Definitely not. Euler family steals. All right, Polly, what do you think the last answer on the board is?
I'm gonna go with Riemann sums.
Riemann sum? Oh, that's actually up there.
Okay, so imagine you've got a wiggly curve. Say the graph of fx equals x squared. You want to find the area under the curve from like x1 to x3. But plot twist, you don't have any integrals yet, just rectangles. That's where Riemann sums come in. Now, with a left Riemann sum, we can take the height of the rectangle from the left endpoint of each subinterval. So like, hey, what's the function doing at the start of this chunk? Bam! Make a rectangle that tall. If you're doing 4 rectangles between 1 and 3, each has a width of 0.5. So then you plug in the left endpoints, 1, 1.5, 2, and 2.5 into x squared. Get the heights, multiply by half, and then add them up. Voila! Area estimate, left-sided style. But hold on to your graphing calculators. We've also got right Riemann sums. Same deal, but now you're asking, what's the function doing at the end of the interval? So you plug in 1.5, 2, 2.5, and 3 instead. Slightly different rectangles, slightly different total area. Sometimes left gives you an underestimate, sometimes an overestimate. It depends on if the function's increasing or decreasing. For f of x equals x squared, which is increasing, a left Riemann sum is an underestimate and right overestimates. And here's the nerdy kicker. As we increase the total number of rectangles, like say 100 or 1,000 or infinity, the left and right Riemann sums both get closer to the actual integral. That's the magic of limits, people. So whether you're a lefty, a righty, a midpoint, or rebel, Riemann sums are your first step into the beautiful world of integration. Stay nerdy, stay curious, and may your rectangles always converge.
Your question is commonly forgotten things.
Keys?
Number 1 answer. Pass or play? Damien, what do you think's up there?
Well, all the time, Steve, I forget my wallet.
That's up there. Mhm.
What about a phone?
Mhm. That's up there.
What about plus C? What is that?
That's up there.
Well.
There's a mystery in the world of calculus. One little symbol, often ignored, frequently forgotten, always watching in the shadows. The constant of integration, plus C. And I'm here to tell you it's not just some math afterthought, but it's the missing piece, the silent partner, the you forgot me in every definite integral. Let's break it down. Say you're doing this, integral of 2x dx. But you may think, easy, that's x squared, done. But hold up, speedster. There's not just one function whose derivative is 2x. X squared plus 5, x squared minus 42, x squared plus pi, they all work because the derivative of any constant is 0. So we write integral of 2x dx is equal to x squared plus c. That plus c is every possible constant that you could have had in the original function. It's like the infinite tail of possibilities attached to every antiderivative. So next time you're solving an indefinite integral, don't ditch the plus c. Respect the plus c, honor the plus c, include the plus c.
That's all three on the board. Last question. Name a relationship that an integral can have with an interval when calculating the average value.
Sit on it!
Yes!